going to jump right in to another episode of Handmade Hero. All right. Hello, everyone, and welcome to what I believe, if I'm not very much in error, it is day 12 of Handmade Hero. It's almost like the 12 days of Christmas, only it is not Christmas. And I'm not sure how that works out exactly, but I think we all know that the 12 days of Christmas are a little weird. If you listen to the song, it's a bit bizarre. And so I feel like we could easily say that Handmade Hero was on one of those days. Maybe you get 5 Handmade Heroes for the 5th day. I don't really know. Either way, thank you so much for joining me here on day 12. If you are someone who has pre-ordered the game and would like to follow along with the source code, you should have gotten a link in your email where you can download it. And when you download it, you want to unpack day 11 for this episode, because you always unpack the previous days to start on the new day. So unpack 11, that is what we are going to be working with today. Now, yesterday I went over all of the basics of platform API design. And basically what I mean by platform API design, there really isn't a term for this explicitly, I don't think. But basically what I'm talking about is the ability to abstract your code away, sort of like pull your code out of being tied to an operating system. And so you can write all of your code so that it's basically used across all the platforms that your game ships on, and then you just have a small piece of code that's basically like a shim, a little platform layer is what I tend to call them, that basically allows the game to run on whatever that platform is. Now, how complicated that is and how efficient that is all boils down to how good of a job you do defining the boundary between the platform-specific code in the platform layer and the platform non-specific code that comprises the rest of your game. And I talked about the philosophy of that yesterday. Please be sure to watch that video if you have not already, because it really does lay the foundation for everything that we're going to do for the rest of the week here. It's basically the driving force between behind the decisions as we make them. And so really what I'm going to do today is I'm going to sort of continue to push a little further down the direction that I started at the end of the last stream when I talked about the platform philosophy that I take in terms of separating things out. Now, if you'll remember, basically what I said is we want to divide things up into two sort of directions. There are services that the platform layer asks the game for, and that's stuff like, what do you want to render? What do you want to play out the sound card, right? What do you want to do for files, like saving files, that sort of thing. So file I/O sorts of stuff. And then there's stuff that goes the other direction, which is also files, because it depends on who's asking for who, and who depends on who's doing what, basically. You know, if the platform layer is asking the game to save its state or something, that could go one direction, whereas if the game is asking to load a resource, that might go the other direction. So that's sort of a bidirectional thing. But also there's stuff like, you know, maybe the game needs to take some profiling information. It needs to look at the system clock or something like that. And that's going to be different on different platforms. So there's all sorts of things like that. So basically we break it down into two types. There's services that the platform layer provides to the game and services that the game provides to the platform layer. And what we did is we started last night after kind of going through all of the philosophy of it and the reasons behind the different decisions, and we basically said the first thing that we're going to do is just abstract our simple gradient. And so we left off, let me go ahead and open the debugger here. We left off at feature parity, basically, where we were. Originally feature parity, but we'd pulled out one piece of code. So we were back to where we used to be. If I grab the little trusty gamepad here, I can still do this sort of stuff with it. It's back to where it needs to be. I can go ahead and do whatever I want to do with it. It's all good. But we have only abstracted one very small piece of code, which is that gradient. The render weird gradient thing is the only piece of code that we abstracted, and that's a problem, basically because we've got a lot of other code that could be platform non-specific that isn't. The example, first of all, the storage of the X and Y offsets that happen when you're moving the gradient around. There is the interpretation of the control events, like what the things on the controller, what various operations with the controller result in as far as the response of the gradient. There's the sine wave that we're outputting that's supposed to basically just, you know, that's the test sine wave. That generation of the sine wave is not platform specific. So we just have a lot of things that are still in our Win32 layer, and what we want to do is move all of that stuff out here so that we can see how all of that stuff is going to flow back and forth, because we made everything in the Win32 platform layer. We made input, we made sound, and we want to kind of move all that stuff out here. So We're going to start by getting sound out, because you can see we did it already with the game off screen buffer. We're going to also now try to get sound out of there. So sound is a little bit trickier, and the reason sound is a little bit trickier is because sound is actually temporal. Now this is a little confusing to understand, and it actually boils down to a technicality that we may or may not choose to explore on the video side of things, but I'll explain it in detail after a little almond milk. Basically, if you imagine what we are outputting sound and video to basically comprise the audiovisual feedback that the user is going to get when playing the game. And basically that is what makes a video game. The audio visuals are what make a video game, because really, if you didn't have those, you would be a board game. That's kind of the difference between the two things. So it's that, it's that audiovisual feedback that really kind of defines, to a large extent, the fact that we are a video game. So it's very important, and it's one of the most important parts, obviously, to think about. Audio is mandatorily temporal, right? Audio happens over time. So when you are listening to the audio output of a game, it is not optional how long it will be playing for. It has to play continuously. If I'm playing a piece of music and I output, say, a 1/16 of a second's worth of music, but I let that play for an 1/8 of a second, which is twice as long, the user's going to hear garbage or silence, whatever was in the buffer, for the other 1/8 of a second, right? For the other 1/16 of a second. The first 1/16, it'll play the music, but the other 1/16, nothing will happen. Contrast this with video. If I play video on the screen, if I put up an image, I can hold that image on the screen for as long as I want, in some sense. And really what will be perceived if I hold it too long is that the frame rate starts to slow down. But you really won't get that same kind of glitching. It's not like it disappears or something like this, right? It's still just lowering the sample rate in some sense that I'm outputting to the person, but their mind does a good job of assembling those images. So if I was displaying at 60 frames a second and then I miss one frame and I end up displaying at 30 frames a second from then on because of some system event or something, so I get slower, it looks a little less smooth, but it did not really appear to be a serious glitch, right? And so what I'm trying to impress upon you here is basically that the video that gets output is a static snapshot in time that is held for some amount of time, and your brain reassembles those and considers them animation. Sound doesn't really have that option. You basically have to output a very large number of samples per second. I mean, if you look at it at the sample boundary, it kind of looks that way, maybe. But really, it's so temporal that you have to basically be outputting 48,000 things a second, and if you don't keep outputting all those samples to tell the sound card what the sound sounds like, your brain immediately hears the error. And it sounds harsh and unfortunate. It doesn't just seem like you're slowing down the sound or anything like that. That's not what happens. Or that the sample rate of the sound dropped. What it actually sounds like is just a flat-out bug. So, so what that basically means is that when we prepare a frame, we don't really need to know how long that frame will be on the screen. It's a little weird to think about, but we really don't. Because we can put that frame on the screen, and let's say our target frame rate was 60 frames a second. We can put that frame on the screen, and if we miss 60, we just update to the next frame. When we're actually generating the next frame, we say something like, okay, let's make that frame, we'll advance the state of the world a 30th of a second, and just flip it later. We'll just move it later on, right? We could recover, in theory. Not necessarily saying you can really do all of this in game code, but I'm just pointing out to you the difference in the output. So with rendering, you're basically just saying, at a particular instant in time, I need the image for this instant in time, just please give it to me. With sound, that's not true. I have to say, I want the sound that starts at this particular point in time, and I need this much of it, right? I need you to give me this much sound. Hopefully that makes some sense. And if you misjudge and you get too little sound, and that play cursor in direct sound catches up to you, you will get a glitch. That's just how that's going to work. Now the reason I say that it's actually not quite true with video, what I'm saying, is because technically you could imagine if your renderer was sophisticated enough to do, say, motion blur, you were doing really accurate motion blur, so that instead of a single snapshot in time, you were actually rendering sort of the continuous motion of everything in the world over the time step, right? Over the entire time that you anticipate the frame to be on the screen. Well, now you've essentially got the same problem that you have with sound. Now the renderer needs to know exactly how long you plan to have that thing on the screen, because it's actually going to do a blur between the start and ending position of all the entities, and if you were to hold it on screen for longer than you should, then things will teleport from their end to their new position, essentially, when you actually go to do the next frame that's at the wrong time, essentially. I know this sounds fairly complicated. We'll kind of drill down to it a little bit more. But basically my point here is that there's a lot of subtlety involved in how you update this. Most games do this very poorly. Most games, Loop actually is very ignorant of what advancing time actually means and what they're actually trying to achieve with it. What they normally do is just measure how much time elapsed, and they like ask the world to advance by that much time. They don't think of it in terms of like what the future is going to hold and that sort of stuff. There definitely are games that do that, but they tend to be higher end. So a lot of games just don't aren't aware of all of these sort of temporal issues that are involved. So anyway, what I'm going to do is I'm going to start out with a very correct but very simplistic model of this kind of a request for audio, and we can use it for video too if we want to. And there are some reasons why we may not be able to get away with this exactly in the end due to the whole audio frame rate glitch sort of things where if we're talking about trying to make sure that we can be as robust as possible in the face of system things that may like interrupt our frame rate or slow us down, those sorts of things. But I'm going to start out with something that is relatively correct in a sense, so that we can basically start there and loosen up to things that are less correct as we need to, if necessary. Hopefully that makes some sense. So what I'm going to do is I'm going to look in here into the game update and render, and I'm basically going to think about the thing that I just said, and I'm going to state what I kind of want to have from the platform layer. And this is a very typical API design approach that I use, and I say this very stringently actually in lectures and so on. Always write the usage code first if you can when designing something like an API. I'm trying to define here what the platform layer gives me, but it's a mistake to try to define that up front. What I'd much rather do is just write some code that uses the things that I think that I'm going to need, look at it and go, okay, the usage code is right now. Now let's go define the API to basically do exactly that or as close to that as we can. So that's what I'm going to do here. I'm basically going to say that, well, I know that I need to do some stuff. I know that I need to, update the sound, right? I need to output the sound. Let's call it output sound or output game sound or something like this, right? I know that I need to output the sound, and what I'm going to need for that is like, well, whatever my game state is, and I don't have that yet because we haven't actually made a game, but then I'm going to need basically how many samples worth of sound you want me to output, right? I need to know essentially some kind of integer which is going to tell me, how many samples. So the sample count to output, right? I need to know that. Then I'm going to need a sound buffer to put them into. And I'm probably going to just lock that format. I'm going to probably just define the format to be 16-bit interleave stereo like we were using in our regular buffer. I don't see any need to make it be sort of like more flexible than that at the time. So we're just going to say that. So it's going to need to know how many samples to output. It's going to need to know where to put those samples. And if we were really going to be, if we were really going to be flexible about this, we would probably put in a way of saying where in time we want those samples to be, so that we can, if we want to, we can skip, if we get into a situation where we're kind of in trouble, we can sort of skip forward. And so what we'd like to do here is basically define something that allows us to sort of say, all right, I don't want you to really assume that every time I call you, I'm just asking for the next set of samples that would be right abutted to the previous set you sent me. I might want you to like overwrite old samples, so we'll advance less, or I might want you to kind of like give me samples that are further out. That's a harder thing for the game to respond to, but if we were really trying to be flexible, that's what we would do. I'm going to not do that yet. I'm going to put a to do here because it's harder for you to understand given the stuff that we've said so far. There's already a lot of stuff in there that we kind of have to cover. It's harder to understand at the moment, and it is harder to implement. So we'll start with the simple case where we're always asking the game to just give us continuous samples. So when we say we want X number of samples, we're just going to plop those down, and then the next time we ask for X number of samples, we plop them down right at the end. They just kind of chain onto each other, and we'll just assume that that's the way it goes. Later, we'll kind of look at a more advanced way of doing it that can do better error recovery. So allow sample offsets here for more robust platform options. So we're going to call the game sound output thing here. We're going to pass it a sound buffer and the number of samples that it should output there. It will do that. And for now, we're basically going to make that just be our sine wave, right? And our sine wave, again, was basically something we pulled out here. It was this Win32 fill sound buffer. And it was pretty straightforward. It basically looked like that, right? That's what it looked like. So this is roughly what we're going to have for that code, and I'll tune that up in a second here. So that's one thing we had. I've got to kind of keep that out of the way of the of my talking head. Oh, Control L actually will do that for me. So that's what I'm going to do for the game for outputting sound. And then the other thing that I want to be able to do here is I want to be able to do the render in the exact same way. But basically what has to happen there is we're going to have to start outputting. We're going to have to start keeping state, and we're going to have to start using a timer to really do anything more complicated here, right? Because you can see we're pretty much platform independent with the rendering, but we're passing in this blue offset, green offset. So that's something that we're going to have to do once we actually get it. So we'll talk about that in 1 second. Let's just focus on the sound thing here. So if I want my game sound output thing to basically, I don't like the order of those parameters. I tend to like things to look a little bit more like they have the object first for some reason. Like they have the struct that holds the things, if that makes sense. So this is going to be a game sound output buffer. And I'm not thinking too hard about these names. Wow, I'm having typing troubles today. There we go, sound buffer. And then I'm going to say sample count to output here. Then we're going to go ahead and actually output those. Now the sound buffer is basically just going to be something that gives us a pointer to the sound. For now, there's not going to be anything more fascinating about it than that. And so really what we should be able to do is essentially just use this code exactly as it is. So we should be able to use this code right here. We should be able to say which sample index we are on. We should be able to go up to the sample count entirely. And then we should be able to, let's see here, is there anything else we want to do here? We can produce our sine wave exactly as we are. So we're going to need somewhere, we are going to need to have our T sign. So for now, we'll just use we'll pass that in and save that, right? There we go. And oh, you know what, the other thing we could do for it too, and maybe this is easier for now. Let's make this a local persist T sign because we're going to move it out pretty much right away. So there's our T sign, so that way we can just use it directly in here. When we output the T sign, we will go ahead and put our tone volume in here as well, because these are all things that we are going to abstract out of the platform layer very shortly. So we got our tone volume in here. That doesn't actually have to be persisted because that can just be essentially a constant. There it is. So that's good. We've got our tone volume. And then we store our sample out. So our sample out in this case is an int16, and that's just going to be coming from the sound buffer, basically. The sound buffer is going to sort of give us the pointer to where we're going to output it. We're assuming the platform layer told us where we should dump our samples, if that makes sense. So we do that, then we increment, and I think running sample index is now irrelevant for us in this code, yes. So basically all I did here was the basic minimal transformation, essentially nothing. All I did was say, I'm going to get a pointer to a sound buffer, right? I am going to take a number of samples to output, right? And then I am going to just dump the samples into whatever is in the sound buffer. That's it. So it's much less complicated than the old version because we're sort of simplifying things for the game. And I'll talk about why I decided to do it that way. So let's see here. We've got samples per second over tone hertz. So this is just, we're not even gonna, let's see. So this is a good situation here actually, and this actually underscores exactly what I was talking about. So you'll notice here I got to a point, I hadn't really been thinking about it much. But we want to know the samples per second here in order to calculate this tone hertz thing. So the tone hertz, we know what we wanted. We know we wanted the tone hertz to be 256, but we don't know the samples per second here in the platform-specific code, platform non-specific code. So that tells me right away, because I want to know the wave period, right? What is the wave period? Let's see here, wave period. Yeah, it's an int still. So I want to know that value. So that tells me, that's basically just a huge clue that we want to store that value in the sound buffer, because people who are going to be using the sound buffer from the platform are going to want to know how many samples per second are playing, so if they have things that are tone-based, they know how many to output. So that was literally, I mean, that's exactly what I'm talking about when I say things like write the usage code first. That just tells me what should be in that. I just know now. I didn't have to guess. I didn't have to presuppose. I didn't have to think hard about it. It just popped right on out. Okay? Hopefully that makes some sense. I'm going to go ahead and start compiling here so we can start knocking down our errors. So I have this game sound output buffer. I've got to define it, obviously. I've got to come in here and actually make one of these. And so really all this is the sample out, right? This is basically the sample buffer. I don't know what we want to call this. Maybe we'll just call it samples. That seems like a totally reasonable thing to call it, because that is what it is. It's the samples. And then we know that we have essentially a, well, you know what we could do too? I like this. I think I like this as well. Yeah, I like this as well. I think I might just roll this in here, right? I might just say that there's a sample count in here, and the sample count says how many to output. Then there's the samples per second, right? And that tells you about the buffer itself. And that, to me, actually looks even better, because then you're just passing one thing. You're saying, here's a buffer, please fill it. You don't have to correspond that in. It's baked right in there, right like that. So that's pretty handy. And it eliminates one whole thing that might happen down here. Let's go ahead and do that. And that looks pretty good. Yeah, I think that's pretty good. Okay, so basically all we have to really do is pass that, and that's it. And then we're going to have to talk about this T sign here, and that's good because that's exactly what I did want to talk about immediately thereafter. Okay, so we're going to have to pass this. We pass our graphics buffer here, but let's pass our sound buffer as well. So let's get that in there. So now it's going into the game. So we'll pass that, and that way it can pass the sound buffer onto the sound filling call. All right, so let's take a look here. Oh, got it, missing semicolon. That's always good. Sign F. So it's right. We're still in test code land. So I want to actually, I think I've said this before, I want to actually implement sign ourselves. I've already got a to-do in there, so that should be fine for the test code, but I would like to go in there and just, we'd like to look and make sure that we're doing a good SIMD sign evaluation or something in there. I don't want sign to be sneaking around doing all kinds of things behind my back. You never know what it might be doing behind your back. The compiler might do anything if you're not careful. Okay, so we've got a sound buffer now. Okay, so our sound output buffer has to get filled. And now you'll notice that what I've done is I've implicitly made a decision here, and this may not necessarily turn out to be a good one or not, but it's the decision that I wanted to make at the outset, which is basically that sound is just not very big, okay? That's something that you have to understand. Basically, if you take a look, let's say you are drawing, like I said, at 60 frames a second. 60 frames a second, well, we know we've got 40, oops, well, if you type right, we know we've got 48,000 samples per second that we're playing. We know that we divide that by 60 frames. That means each frame we are outputting 800 samples. Okay? We know that each one of them is 2 bytes long. That's 1,600. We know that there are 2 of them for stereo. That is 3,200 bytes that we are writing. 3,200 bytes is like the most insignificant thing a modern processor has ever seen. We are talking about processors that can move gigabytes of data a second, so 3,200 bytes is literally irrelevant. So what I have elected to do here is suffer an extra buffer copy for those 3,200 bytes per frame that will be going out the wire. Basically, I'm going to do an extra buffer copy there because I would rather present the game with a cleaner interface of just writing into a single buffer rather than forcing it to inherit the direct sound dual write problem with the ring buffer, because that's a complicated thing. It's easier to get wrong, and I don't want to pass it on to the game, especially because there are other platforms that don't have that janky ring buffer nonsense going on. And in those cases, this will be just as fast because it can write directly into the location it's supposed to go. And so basically, really I'm just saying I don't think this is going to be a performance problem, so I don't want to pass this on to the application. I just don't think it's going to matter, and that's always a judgment call. There are plenty of times where you have an opportunity to do something more efficiently, but you incur a bit of complexity, and it really is a judgment call which one of those you take and which one of those you don't. In most cases, I tend to prefer to do the cleaner thing if I can, if I know that it's not going to be too expensive, and then later, if it turns out to be a performance problem when we are actually measuring it, then I will go and introduce the added complexity at that time. That usually is a smarter way to go, especially because it means that you already have the simpler case working correctly, and so when you implement the more complex case, you're just debugging it versus the simple case instead of writing it completely fresh the first time. So it tends to actually be a good way to develop even if you weren't doing the methodology that I was talking about, which is make sure it's actually a performance bottleneck before you incur the cost. Okay. So we've got our sound buffer here, and what that basically means is that if we take a look at, excuse me, if we take a look at what's going to happen down here, we basically need to first get some memory that we're going to store this sound in. Now, we don't even actually have to allocate any memory because we're only actually going to be doing whatever our frame rate is. And our frame rate at the moment, I think I'm leaning towards maybe doubling that number. Instead of 800 samples, I'm gonna say that maybe we'll try to run at something like something more like 30 frames a second. Because since we're going to be doing software rendering, I think trying to hit 60 frames a second is not going to be realistic in a lot of cases. So 30 frames a second might be more what we target. So basically what I'm going to do is going to ask the game for a buffer that is going to be 1/30th of a second's worth of audio each time I ask it. So basically I'm going to go in here and say that the sound buffer, right, and I'm going to look, take a look, oops, that's not good. I'm going to take a look at the actual stuff I got to put in here. So the samples per second, that we've already got. That's fine. The sound buffer sample count, that's going to be the samples per second divided by 30 for now. Again, this is all just sort of layering the code in. This is not supposed to be final shipping code or anything like that. I'm just showing you how we do these transformations in steps. So I'm going to go up here and say, okay, we have the samples per second as well. It was right here in our sound output routine. So I'm going to go ahead and put that in here. There we go. And then the samples, I'm just going to put these right on the stack. I don't really need to allocate any memory for them. There's no sense in doing that. So basically I know that I just want this many of those, which is pretty trivial for me to do. I can basically say that I just got an N16 sample count samples, and I will actually just say that I have some of them, and we'll basically say, I don't know, for now we'll just say that we've got this many of those samples. So basically, that is really all I wanted to do. It's pretty straightforward. And then this is going to get cleaned up in a second here to use something that's a little more flexible. Because the problem with doing it right on the stack is that unless we use a function I have not talked about yet, you can't actually make anything that's on the stack be parameterized on something that isn't a constant. Now, I could, of course, actually introduce a constant for it, but I don't see any reason to because I want to talk about how you do that also separately. All right. So if we do that, when we call game update and render, I can pass the sound buffer now into this, which I will do. There we go. And in theory, this will still run, even though we've kind of just done some janky stuff. Oh, maybe not. Maybe not, ladies and gentlemen. As I say that, I'm totally lying. I did do the right number here, did I not? This is literally just the jankiest code. I mean, yeah. I say it oftentimes, but do not, this is never something that should be left in a shipping program. I'm literally just trying to show you how to push the platform layer kind of up there. Just want to make sure I didn't type something stupid before we go. Okay, put the samples in there. That's good. I called the thing with the sound buffer. That's good. I don't remember what we wrote so far in here. Game output sound. We got the sound buffer. Samples per second, the tone hertz. We look at the samples there. The sample out. That's going to the sample count. Oh, this is... right, that's the right value in there. Sample index goes through. It's outputting 2 of them. Yes, fantastic. This is just dumb. We're stereo, of course, so we need that. There we go. Okay. Good to go. So one thing that's kind of nice about that, and I'll talk about that in a second, is you notice when I forgot to multiply that, you'll notice that the debug library caught it for me. So basically what happened here is they put some checking code to see if you overwrote memory somewhere, right? And that's pretty helpful. It doesn't happen that frequently, especially if you're not trying to stream at the same time as you're programming and you're paying attention, but it does happen. And so one of the things that's nice is if you do have things that catch buffer overruns, it's something that helps take, like a lot of people are afraid of pointers and afraid of languages that have them, specifically because you can do stuff like this. And you are afraid of shipping things that have these sorts of bugs in them, and that's legitimate. But there's a lot of ways you can actually minimize those things, and we haven't gotten to any of that yet, but this is already one that's even just built into MSVC, basically. I didn't have to write that, right? It just caught that for me. I didn't do that work. It just caught that buffer overrun for me. And so then when I fix it, it doesn't happen anymore, right? And that's pretty cool. We're going to be looking at ways of doing things that are a little more advanced than that to catch things that are possibly a little harder to catch. But for now, it's just worth mentioning that that's kind of a nice thing for people who are going to be a little more scared of pointers. I'm never scared of them. I just like throw them around, and then I'm like, okay, when it's time to start tightening things down, I bounds check my things, and I just go through a set of things that kind of rigorously tightens things up. So I don't really worry about them. It really doesn't end up being a problem. But for people who are scared about things like that, it's worth noting that there are a lot of tools that help you, and that was one of them that just helped us. Okay. So right now, we're still getting a sine wave from the actual platform layer, right? We've given a sound buffer to the game, right? And the game is doing the sound, it's generating sound for the sound buffer, certainly. But we have a problem, and that problem is that basically we are not using any of the stuff that comes back. We are still generating the sound thing, all of the sound code ourselves in the platform layer with Win32 fill sound buffer. So what we'd rather do now is we'd rather use that Win32 fill sound buffer code, right, to actually grab, instead of the sine wave, grab out of our buffer. So I can do that pretty simply, right? I can just pass the sound buffer itself over to this thing, right, into Win32 fill sound buffer. And now, instead of this ever actually computing a sine, right, it can instead just read from the buffer that we already had prepared for it in the platform non-specific code. So I can say game sound output buffer, it's basically source samples, maybe let's just call it source, like that, source buffer, I don't know, whatever you guys want to call it whatever you like, anything you like. It's fine with me. Okay, so let's say we have the source buffer there. Basically what we're going to do is we're just going to pull from that source buffer instead of the sine wave. So we got an int16, we've got sample, I guess we'll call it source sample, and maybe we'll call this dest sample, right? We'll just change the nomenclature here. And that's going to be the source buffer samples it's going to pull from. So in here, all we're really going to do is we're just going to copy, right? We're just going to copy every last thing. So we're just going to do something like source sample plus plus, like that. Basically this is all we're doing. We're just copying from one buffer to another. We're just flat out copying. Nothing else is happening of any interest to anyone for any reason, right? Okay, so that's it. That's all that's happening. Star source sample plus plus. In fact, you know what? I don't even need to do this. I can just copy this one up here. We don't need the sine stuff at all. I still have draw this out for people. I don't know if we drew it out or not. If we didn't draw it out and you want me to see you draw it, now would be a good time to tell me. So we're basically doing that copy. We're doing it twice. We can collapse these two loops soon too, actually. You can see they're starting to get even more ridiculously simple and related to each other. So that's really mostly all we need to do to change it from outputting the stuff that comes from one, from outputting stuff that comes from the other. Now, what we do have to do is deal with our startup a little bit differently, because we initially filled the sound buffer with stuff at the start to put a sine wave in there to kind of front load it. But that's not really what we want to do, right? We don't want to do that. What we want to do instead is just basically clear it at the beginning, right? We just want to clear the whole buffer. So what we really want is another function here, which is basically like Win32 clear buffer, something like that. And so what we want to say is like, hey, why don't you just take the entire buffer, flush it with zeros, and then we'll start writing sound into it at some appropriate point in time, right? So assuming that we do that, Win32 clear buffer, what we basically need here is something that goes ahead and does that clear, Win32 clear buffer. Let's take a look here. So we're going to global lock this thing like this, right? There we go. And this is basically doing the exact same code. Nothing really doesn't need bytes to lock or bytes to write, really, because we know pretty much that we're locking the entire buffer, right? Absolutely everything is going to get that treatment. So the bytes to lock will be the entire size of the entire thing. So we basically want to basically just pass everything. Give me everything you have from the start all the way to the end of the buffer. So that'll lock that. It'll give it back to us. And then we just need to clear it, basically. And we can use this same code here. We can basically say, well, we'll go ahead. We'll take that. We'll take a look at the sample count. Well, actually, we don't even need to be in samples anymore. We can just be in bytes. So we can literally just take something that looks like this. We can say byte index equals 0, byte index less than that, byte index plus plus. And we can basically say that this is going to be a uint8, like that. We're just going to basically clear everything, the entire buffer, to 0. Does that make sense? Hopefully that makes sense. So we're basically just saying, all right, clear everything. Everything you've got, every last byte in this buffer should be set to 0. So there you go. Now, I don't anticipate this actually ever happening, because it should just give us back one contiguous region since the thing isn't playing yet and we're locking from 0 to the secondary buffer size. But just in case something wonky happens, I might as well handle it. We'll see. So okay, we got the death samples. We can take region 1, go through all of region 1. We write zeros into it. Same exact thing here. We're doing it by bytes, not by samples this time, because we don't care. This could also be if, since we're trying to call as little library functions as possible. There are functions like memset built into the C standard library that would set memory to a particular value and clear as well. But we're just doing it manually ourselves. Okay, so then we go ahead and we unlock the buffer after we're done with it. So there you go. That'll lock, do the clear, unlock, right? Nice and clean. So hopefully that'll clear our buffer. Yep, there we go. And now we'll actually sort of be playing our sine wave, but there's a bunch of jankiness in here that now we have to clean up. I think it will probably actually play the sine wave, but it's going to be buggy, if that makes sense. Oh, got to finish this as well. So okay, yeah, sorry, forgot that we were in the middle of a second function there as well. All right, so Win32 fill sound buffer also obviously has to work. All right, so we're going through our samples. We have our source buffer here. We're doing interleaved, which is correct. Oh, okay. So the other thing that this is just the thing that I was about to say. I guess I can't run it till I actually clean up the thing I was about to say. So what I was going to say is, so now, however much we tell the game to fill, right, that is essentially going to be determined by, our frame rate if we're trying to actually hit the frame rate properly. But the problem is the thing that we were using for our write cursor is just taking wherever the target cursor is and looking at how far we would have to write to fill up to that point, right? So what we actually have to do is we actually now have to think about where in the sound buffer we actually need to start putting things, and then we need to just always make sure that we update the right amount of samples. So there's two ways that we can actually do this, and maybe I should do the other way of doing it first. Instead of saying let's always output the number of samples that will correspond with the frame that we want, what we could do instead is say let's just use the way we were doing it before and ask the game every time essentially to output enough to fill to the point that we want. So basically what we could say, right, is we could do this here and basically say, all right, if sound is valid, like this, like that, sound is valid. What we could do is do the computation that we were going to do before. So basically, assuming that the sound is valid, then we actually ask for that many. The reason that I wasn't doing that quite yet is because I wanted to do it without having to show you guys how to allocate stuff on the stack. But I guess we're going to have to, because at the end of the day, we can't actually call this thing if it's not set up to work properly. It's just going to crash on us. We're going to have a huge problem there if I don't do it properly. So, what can you do? I was trying for something. I got to backtrack on it. I got to backtrack a little bit. That's what, what can you do? So anyway, if we take a look at these guys here, and we basically say, all right, we've got this stuff, we're going to compute it. So we're essentially going to compute all these things. We're going to compute the byte to lock. We're going to compute the target cursor. There we go. We're going to compute the bytes to write, and we're going to save them, right? Oops. That's not right. There we go. We're going to compute the bytes to write. And we're going to save those things, and we're going to say the sound is valid, assuming that we were able to actually do that. Assuming the sound is valid, then what we want to do here, essentially, is we want to go ahead and ask the sound layer, the game, to output the number of samples we actually want, because we now know how many there are, right? There's going to be bytes to write will basically be the thing we want, and since we're asking for it in samples, we basically need to divide that by our sample size, right? However big the bytes per sample is. So basically what we're doing here is we're saying, okay, the sample count that the game is supposed to write is going to be the bytes to write divided by our bytes per sample, right? It's basically 4, dividing by a stereo paired 16. So the problem with that is this thing ain't going to hold that. Now, I mean, I could be cheesy and do something like this, which would be absolutely huge. That's not what I want to do, so we're not going to do that. But at the moment, we can probably do something. What is its sound output? There we go. So let's see here. All right, but first, maybe I will just do it this way, just so we can debug this code. I slammed a lot of code out there right now. I appreciate that. So we got to kind of debug it, get it working properly, step through it, make sure everything's kosher, and then we'll talk about this nonsense right here. That seems like a reasonable thing to do. All right. So hopefully, as you can see, we're back to basically exactly what we wanted. The only problem is we've kind of dropped our feature parity again because we no longer pass the tone hertz in. The tone hertz is not dependent on the stick, which is what we wanted. But we are actually generating our sine wave. As you can see, sine f is no longer called in the platform layer at all. So we know that basically all of our sound is now coming from game output sound, which is what we wanted. However, we've still got some really crufty stuff here, and I want to step through that code. Maybe what I'll do is I'll push it. I have one more thing I maybe want to get to today, or maybe not. Let's see. I'm gonna push forward a little bit more. I realize there's a lot of stuff in there, but in the Q&A we'll go over it again. Just to let you know. So let's take a look at maybe one other thing first. So the other thing that I want to do, right, is I want to move that tone, like I want to move sort of the. You know what? No, it's going to be tomorrow. I'm sorry. I'm thinking. I'm kind of running forward in my head, and I'm just thinking about it. And I'm like, it's going to be too complicated for me to talk about all the things I want to talk about for the next thing that we're going to do. So instead what we're going to do is I'm basically just going to go ahead and pass that tone hertz to get our feature parity back, and then tomorrow we will look at getting all of those values, basically that we're passing here, right, to game update and render. I'll look at extracting all of those back out again. So tone hertz comes in here, because none of these should actually be being passed from the platform layer at all. None of that should be happening, but I kind of try to do this in waves so that I don't overwhelm people with too much reorganizing of the code at once, basically. So the tone hertz is now passed in. We're good to go with that. So in theory, we should be back to feature parity. Yeah, that's what we wanted, so that's all good. So let's go through here now and take a look at all this crazy code I added, and then I guess the most important thing to talk about will be that stack allocation. So, okay. I have choices here about where I want to store this sound stuff. Now, in the future, I don't really want it on the stack. The stack is not probably where I want to actually put this stuff. But, like I said, while you are moving code around and doing stuff and we're trying to get all the architecture in place the way I want it, I don't want to spend a lot of time thinking about things like this. You want to basically, and again, this is sort of the sort of thing, a lot of people talk about garbage collected languages and that sort of stuff, and they're like, how can you possibly deal with languages that don't have these things and that sort of stuff? Well, the answer is, actually, I just don't worry about those sorts of things till I'm ready to kind of tighten them down. And in the interim, there's a lot of techniques you can use to not really worry about memory, to just kind of have it happen however you want. And you'll notice that we kind of haven't had any problem with that so far. We've basically never had to really think about memory at all. We're just like, most of the time when we're thinking about memory, we're talking about like writing things into buffers and stuff like that, that you would have to think about anyway, even if you were just filling them as arrays. You can still do things like buffer overruns in languages that don't have pointers by just trying to write outside the bounds of an array or something. That's still a bug in your program. You shouldn't have done it. And so the fact that maybe the language doesn't crash as a result isn't much of a, doesn't really help you because your program still just doesn't work. So anyway, point being, what I wanted to talk about here is if you just are trying to get stuff working and you're just kind of screwing around, there actually is a function, depending on the circumstances, called alloc. And basically, I don't actually know, to be honest with you, whether they've standardized on an actual name for it that always works, or whether you have to choose whether it has an underscore or not based on whether it's on a certain platform. So I usually abstract this away. It's actually in the platform include files I do it. But it doesn't matter here because we're actually just calling the Windows version, so we only care what theirs is. And basically, what this allows you to do, you can basically say alloc, and you can give it anything you want, just any size. So that's like a size that we want. We want, let's say, that many int 16s, right? That's how much we wanted. And basically what that will do is that will just allocate on the stack for you that much memory. And the stack, if you think about it, is kind of a little like having garbage collection, right? If you don't care about something, you can throw it on the stack and you know that it will go away when the function is done. So it's kind of automated in that sense. If you're a C++ programmer and you like things like smart pointers or things like that, it's very similar, right? There are things that are going to go out of scope at the end of a function and just clean themselves up so you don't have to think about it. I don't actually tend to use code that looks like this in shipping code very often, because I prefer to do things slightly differently once I have everything the way I want it. I tend to go in and do a little pickiness, a little OCD-ness that results in usually not having allocs happen in code very often. But when I'm just developing code, I will often throw in stuff like that because, hey, I just like, okay, I know that that'll allocate the thing that I wanted, right? And it'll be fine. Where was the actual, where was this guy defined? It is in malloc.h. There we go. malloc.h. And I am going to go ahead and put that down here. There we go. Probably put that actually standard IO. Okay. And then I should be able to compile now, hopefully. Oh, right, and this returns a void star, of course, so I have to cast it to the type that I wanted. All right, so that's basically just a way to do that allocation, or not. All right, so I guess this is basically saying that I can't make something that big on the stack, is my guess. Maybe this is one good reason not to do it. What does it say? Yeah, Stack Overflow. Okay, so basically, this is one of those things where we looked at this before. If I want to start playing around with alloc, I'm going to have to actually deal with, I would actually have to deal with having that stack size larger, which of course we can do if we just want to play with it. But again, I just wanted to kind of show you that. So I don't really know if that's worth doing. Like I said, I almost never use alloc. I only use it when I'm just playing around with stuff. So if I'm going to allocate something that big, it really wouldn't matter much. I don't know. We've got 12 minutes left, so let me just go ahead and do it the real way. The Stack Overflow is kind of like a message to us that says we should actually just do it properly. All right. So what I want to do, and I wanted to do this before, is basically we have our allocation up here, right? We've got our virtual alloc, right? Right here. This was our virtual alloc that created the bitmap that we actually needed for our div section, right? And so if we wanted to do something trivial down here where we actually just want memory for our buffer, the easiest possible thing to do, the thing that's just the simplest, is just to do this buffer once, right? And I was trying to avoid actually going into this, but I realized I got plenty of time, so I might as well just do it because it's the right thing to do and it's what I wanted to do eventually. So basically all I really have to do is I can just do this, right? And I can actually virtual alloc the thing that I actually wanted originally from Windows directly. And basically what I can do is I can say, why don't you give me something that's the entire secondary buffer size? Because I know that I never will need to output more sound than our entire buffer size. And that just gives me a backing store now that I know will always be big enough to fit the thing that I needed, right? So basically, I'm doing this, you know, we're good to go. I always have the memory. I don't have to worry about alloc A being too, you know, big on the stack. I don't have to worry about any of that stuff. This is just the memory that I wanted, right? So that's pretty straightforward. It's a very easy thing to do. But one of the things that I like to do too is I don't often like to necessarily have all these virtual allocs around. So what we will probably do eventually, and you'll see this very shortly actually, is we'll pool these virtual allocs into a single virtual alloc that just gets us all the memory that we wanted, and then we will subdivide it out. But for now, that is really all we had to do, because if you think about it, we got the memory for our bitmap up here, we got the memory for our sound buffer down here, and basically what's happening is we know that we never need more than that memory, so it doesn't actually matter when we get down here. It never actually matters how much we're going to ask the game for. We could ask it for a lot, for a little. We know that it will always fit in that buffer that we got because that buffer could hold, if it needed to, basically all the stuff that was coming from the sound output, right? That there isn't any way to play to direct sound more than the buffer size that we originally had, and so we can just allocate it this way, right? It's really, really straightforward. I hope that makes some sense. But basically all we're doing, I don't know why that always starts off at that. Yeah, it's kind of weird. It looks like, for some reason, my gamepad has this weird thing where like it always starts off not centered or something weird like that. I'm not sure what is actually going on there. It's weirder too. I don't know if you can see this, but the gamepad itself isn't even like initialized. You can see that? You notice how it lights up when I launch the app? Yeah, I haven't played much around with this gamepad. I suspect that basically we just have to go in and tighten up that X input code a little bit, which we'll do a little later on, but it's kind of wonky. Anyway, so that's really all that's going on here. So let's take a look at what's happening when we step through the code, right? Basically what's happening is that at startup time, here we go, we opened our window, we initialize our sound output with dsound and clear out that buffer, right? The buffer is gone, it's cleared. Now what we do is we say, all right, we need to allocate a backing store that's basically some place that we can put the samples, so that the game can stuff the samples, that we can then copy out into the ring buffer for a direct sound. So it's that extra copy. I said it was a little inefficient. It is, but I didn't want to pass that complexity onto the app. So basically we get our sample buffer there. We go into our loop, and each time through our loop, okay, after we're done processing messages and the controller obviously, we go and we say, okay, where is the right cursor at the moment? Tell me where it actually is. And that will basically give us back how much we want to write into the sound buffer. We will then create a faux little wrapper here that just says, here's the samples per second we were using, here's how many bytes I want you to write out, divided by the bytes per sample to give you a sample count to write. This is basically telling the game how many to write. We're going to go ahead and set up the bitmap memory as well, like we did before. We then tell the game, we want the bitmap, we want the sound. It goes ahead and does its sound. It looks at the samples, it writes them into that buffer using the sine wave, right? Does the gradient like we did before. Now, assuming that the sound sort of request for the pointer worked before so that we know we're actually outputting sound properly, we'll go ahead and fill that sound buffer. We'll come in here, we'll copy out from the samples that the game stuck in the buffer, we'll copy those out, and we'll use the split ring thing, so we'll basically turn it into the right thing for the ring buffer if necessary, and then we will unlock the buffer and it will play, right? That is all we did. Very, very straightforward, very, very simple. Sorry that I sort of gave you a little red herring with the alloc A there. I thought it might be a good time to introduce alloc A. It wasn't, because basically our stack just isn't big enough for something that large. That is a fair number of bytes because, you know, I was allocating the entire second's worth of samples. If we were just allocating just the 60th of a second or just the 30th, that would have probably worked fine. But when I changed to doing the whole thing, that's not going to fit. We'd have to up our stack size, and that seems stupid because I didn't even really want that to happen. And so it seemed like a bad idea to kind of go down the alloc A route just because I had started on it instead of switching to the correct thing. So basically what we're going to do, this is going to get pooled, pool with bitmap virtual alloc, and that's basically all we really need to do there. So that's mostly everything for sound output. And so if you look at basically what we've done, we've got graphics output moved over, we've got sound output moved over. So basically all we're going to do next time is look at how to get input over there. And then we've got all the platform services over, but we still have one more thing, which is memory, and we're going to have to talk about that probably the day after. So unless input goes extremely quickly, which I don't think it will, we'll do input tomorrow and then we'll do memory the day after. And then we should be in really good shape. We're kind of in game land at that point. So now one thing that I wanted to talk about that's a little bit iffy here, right, is this is still kind of janky, because if you think about what happens when we come through this code, and we've got 5 minutes left, so I just want to kind of talk about it. We're clearing the direct sound buffer, so now it's all filled with zeros. And then we're starting it playing, so now Windows is just playing. What I would like to do is say, well, the first time we start filling it, we don't want to fill it basically from the beginning, because that doesn't make any sense. There's no need to do that because we haven't actually done anything yet. What we want to do is start filling it somewhere in the buffer based on where direct sound is at the time, right? So what we want to do is basically in here, right? When it figures out this sort of stuff, and it says, you know, where the target cursor should be, we want to always do the lock from like the right cursor or something. We'd want to just put the sound out there where it should be. Now, there's a problem that we run into as well that's worth thinking about, which is when we look at this and we say, when did we call get current position to get the right cursor, right? Well, we know that we're going to call that. We need to figure out how much sound we want to write if we're going to actually look at the sound card to see how much we should do. Well, the problem there is by the time we're then going to go through, when we do that call, Windows will tell us basically right here where is the sound card playing at that time. But then we're going to get down here, and what's going to happen is we're going to call game update and render, and that's going to take a lot of time. Game update and render is going to take like a 60th of a second. So we can fully expect that this will be like 800 samples out of date by the time we get down through this, right? So we kind of have a mismatch there, and we need to start accounting for that. That's sort of what I was saying is why we have to start getting more advanced with these things, because there's actually a lot of finickiness that happens there that we have to think about. Now, one way to solve that problem, obviously, is to always be very latent, to always be very far ahead. So for example, we could go in here and we could say that, you know, we're always going to start, we're going to try and be way ahead. That latency sample count is going to be like really fairly sizable or something like this. But again, these are all things that we kind of have to look at a little later when we start to sort of tighten that down. For now, we've gotten things working the same way that they did before, and that's fine, but that's not going to cut it in the end. So basically, I'm going to drop a little to-do in here that's basically like tighten up sound logic so that we know where we should be writing to and can anticipate the time spent in the game update. Because that's going to be pretty important. This is, like I said, it's pretty janky right now. It's not what we would want to do. It's good for playing out a sound wave, but in terms of actually robustly keeping the sound going, it's not going to be, and there's nothing, basically the code is structurally correct in how it's getting the data back from the game and how it's filling the sound buffer, but it's essentially, it's logistically incorrect because it's asking, the way that it's doing its target computation just isn't good. It was basically that's what we did to get things working, and that's fine, but we gotta basically take that up a notch. I'm not gonna start doing that now because we're almost to the Q&A, but that's basically it for that. So let's take a look. I can't remember if there's anything else we're supposed to do today. I don't think so. Well, I guess at the very end of the stream here, I might as well go ahead and do one thing that someone asked for. They were asking to maybe have this have an if not exist. Basically in our build.bat, you'll notice that it always says this line, and that was annoying somebody. I guess they were a stickler for checking first. So we can do a thing here. I never do these. Do you do it like this? I think that's how you do it. So you just do if not exist, the directory, then you give it the make dir, and that works. So I'm pretty sure that works. I guess I'll double check that it works because for all I know, it might not. So inside that build directory, if I was to temporarily say rename build to build foo, would this guy, where is it? Would it work? Let's take a look. It did. Okay. So that's fine. Let's go ahead and nuke that. Oops. And then we'll rename it back. Okay, so hopefully that takes care of anyone who was getting sort of thwarted by that, or getting sort of annoyed by that coming in there, that repeated attempt to make a directory when a directory already existed. Okay, so we now have both sound and video happening out in here. And we basically, our video is actually pretty okay. There's some things that I want to change, just finish up about that as well, but we could write a whole renderer in here and we'd be fine. Our sound still needs a little more tightening. Whether we do that tomorrow or not, I don't know. I probably would rather get the input and everything over there and then maybe do next week a little sound tightening. Just go through and kind of have our loop a little more laid out. But we're pretty good. We're in pretty good shape. I don't think there's anything left dangling here. I think it's pretty good. I think it's pretty good. So I'm relatively happy with that. I think now is a pretty good time to go ahead and start the Q&A. So let me see if anyone's got Q&A out there to ask about. Let's see. Let's see. Trying to figure out where the questions start. You're allocating a new buffer every frame. They don't get freed until the function exits. Sorry, I'm not sure. That doesn't sound like a question, but that's okay. Let's see. This may be getting a little ahead of things, but will we want to use allocate to do things like store pointers to game objects that are local to the player? No. So allocate is literally just a local variable. So basically all it is, I probably shouldn't have shown it today. Like I said, virtual alloc was really the right thing there, and more specifically, pooling these allocs up above is going to be the right thing eventually. So I probably should have gone there first. And you know, one of the things that's hard when I'm in the stream, I got to make split-second decisions about what I decide to try to show you, and I look for opportunities to show you things that might be appropriate, but I don't always know if they will be, right? Like I've never tried to allocate a 1-second sound buffer on the stack before, so for all I know, that could have worked fine. Although I guess we did kind of check that. I don't know. I'm actually surprised that didn't fit. Probably should have, but it would have been just barely. All right, it doesn't really matter. Point being, what you have to remember about allocate is basically it goes away whenever a local variable would have gone away. So if I do an allocate here, let's say I do an int star foo equals allocate, right? And I say that I want, you know, to allocate an int. This is basically, you know, this is basically what's going to happen. We'll show you. There we go. So our foo, let's say we wrote to star foo equals 5, like that, right? There we go. So basically what's going to happen is when I come in here, let's take a look. Hello, there we go. Let us go to where I wrote that. So what's basically going to happen is when I come in here, and you can actually see in the assembly here if I dump into it, right? You can basically see that no actual allocation happens, right? Nothing actually occurs. What happens is it just moves the stack. It just expands the space in the stack just like it would be for a local variable, right? So it goes ahead and expands the stack, and then basically what we end up with now is our foo pointer, right? That's the pointer to foo, right? Y offset is right before it, right? You can take a look at what the address of Y offset is. They're right next to each other, right? I mean, they're not abutting, but they're basically in the same space. So all that allocate does is just says the same place that I'm storing these local variables for the function, I need some memory that I don't know how much it is. So I'm just going to pass you a number, and I want you to give me that much, right? What that means is that literally at the soonest possible instant, right? So this is the scope that we're in. We're in this scope. So if we go down here, right, that's here or whatever. I can't actually set a breakpoint there, but you know what I mean. That's like right down here. As soon as the control flow reaches the end of this and exits it, it goes away. That memory can go away. The compiler might keep it around. You know, it's at the compiler's discretion, basically, exactly when it cleans up the stack. But at the very least, when the function exits, it's going to reuse that stack for the next function call. So you cannot put anything at all in an allocate that you want to keep. Nothing that you want to keep. You basically have to only use it for transient things, just like local variables. Now, there are some exceptions to that. Obviously, if you were to allocate in the middle of the main, which never exits, essentially, then you kind of have it forever. But at that point, it's also the only reason to really use allocate instead of a regular alloc is because you expect it to go away. I could have just called virtual alloc and got the memory and kept it, which is what I ended up doing, right? So there is no real compelling reason to use alloc unless you are trying to use that stack cleanup to get rid of the memory for you when you're done with it, right? So it's a thing for temporary computation, and that's really all it is. You can't use it for storing anything permanent. There we go. Let's see. If the DS buffer lock fails, you'll pass garbage vars to the game code update via the game output buffer setup. Yes, that's totally true. And I can put a to-do in there for you. Like I said, this logic kind of needs to go away. But if it makes you feel more comfortable, right, you can do make sure this is guarded entirely, right? Because yeah, we also don't know exactly what's going to happen. I mean, I suppose, one thing I could do if it makes you feel better too is I could do this, right? And that would be fine as well, because then if this does fail, this will get set to 0 here, and that'll be fine. But again, this is getting vaporized, so I wouldn't worry too much about that because this computation is not right. It needs to get changed, so we'll do that shortly. When you say 60 FPS might not be feasible, do you mean for non-PC platforms or specifically? So I mean for non-hardware acceleration. Or it might even be for hardware acceleration. I mean, basically, we don't know going into a game what's going to be feasible frame rate rise because there's a trade-off there. 60 frames a second means you have worse looking graphics. Period. I mean, that's just by definition. You have half as much time to generate the graphics. So basically, if you're at 60 frames a second, they will look half as good as 30 frames a second. And it's actually even worse than that because some things are constant and don't scale depending on that. And so like there's, at the risk of getting into something that's a little bit too off topic, what I mean is basically if you imagine you have a post-process and a pre-process that happen before doing the actual graphics, like say a post-process filter on the screen. Well, that filter is going to be the same amount of time no matter whether you're doing it at 30 frames a second or 60 frames a second. So basically, if you expand to doing something at 30 frames a second, it takes up, the post-process takes up a lot less of a fraction of the frame time than it did at 60th of a second. So the actual time you have to do all your render stuff actually goes up by more than a factor of 2. That's a little confusing. It's probably a bad explanation. Table that for much later when we talk about rendering stuff. But point being, we may decide not to be 30 frames a second even with hardware acceleration if we want the graphics to look better. Because for any given game, you have to make a call about whether 60 frames per second is worth it or not. Now, of course, it'll always be able to run at 60 frames a second 2 years later when all the graphics cards are way better and stuff, right? But I mean, at launch, at the target platform, normal, person does not own 50 SLI graphics cards in a giant water-cooled case machine, then maybe we'll decide 30 hertz is better because we can make prettier graphics or something. Let's see. For a clean build, blowing away build each time would be nice, but the solution file is there. Are we not worried about clean builds? Yes, we are not worried about clean builds at all because we rebuild everything every time. So build clean is something that you only have to do if you are doing partial rebuild, right? Since we build everything every time, we don't care at all. We don't need a clean build. We never will have that thing where the build gets weirdly out of date. It solves all those problems if you just build with a batch file that builds everything. So we don't ever have to worry about a clean build. So the fact that the SLN is in there doesn't matter to us because we're never going to have to clean out that directory. Now you could move the SLN somewhere else if you wanted to. That's entirely up to you. Yeah. The allocating every frame was your bug with allocate. You were calling it in a loop. That's actually fine. So basically, it doesn't matter if you call allocate in a loop because allocate goes away at the scope, I believe. unless I'm wrong about that. So for example, if I want to, but maybe that's not true. Maybe I'm wrong about that. I don't use alloc very often. I'm trying to remember the last time I actually used alloc. So I'm just going to go ahead and allocate something relatively large here and see if that's actually true, just so I can know for sure. Yeah. Okay, so basically, I think you're actually right about that then. That does suggest that that's true. So I was assuming that that would get cleaned up on the scope, but it only gets cleaned up on the function. I definitely have never called alloc in a loop before. That's definitely true. And I hardly ever call alloc at all. But it looks like, okay, yeah. So basically, I guess that's a good catch. So basically, let me take a look here. Yeah. Okay, so, well, does it say that? I don't know what it says. Let's see. Yeah, okay, so basically it doesn't actually scope the alloc. It only scopes it to the function. So basically, okay, so basically all that's going to mean is basically it's only going to free when you leave. So I should have, yeah, so that makes sense. So okay, that all makes good sense now. That was just me I've literally never called alloc in the loop before. So I had no idea what it would actually do in there. So if we had done it right here, basically, this is not in a loop. If we did it right here, that suggests it should have worked. I just kind of dropped it in where it was logically. Let's go ahead there. So I should be able to instead do it this way. Thank you, by the way, Dyslexic Deity. Or, wait, no, who was it? Yes, Dyslexic Deity. For that catch. Having more eyes on the stream is so good. Like, I probably would have just moved on and been like, whatever, because I never use alloc, and I would have just been like, whatever. But that's, like, cool. Like, I learned something, right? And that doesn't happen when you're just programming by yourself. Yeah, okay, so that's totally awesome. So basically, we could have used alloc. It was not a problem size-wise. We could have used alloc right here instead of virtual alloc and put it on the stack. The problem was that I put it in a loop because I was just assuming, oh, the compiler will clean it up when we exit that loop, right? When it comes down here, it'll just grow the stack, shrink the stack. To be honest, I don't understand why it doesn't do that, but I guess it's better that way because the compiler has more options if it knows that it only has to clean it up later. So that means you basically can't ever use it in a loop, but that's okay because like I said, I've never actually used it in a loop before, and in this case, I didn't even want to use it in the loop. I just had dropped it in where the loop was because I wasn't thinking about it. Because we don't actually need it in the loop for any given reason. We just wanted to allocate the buffer one time, so that's fine. So that's actually totally fine. You could use alloc there. I'm not probably going to leave that in there because I want to use virtual alloc eventually. So I'll delete that. But thank you very much, Dyslexic Deity, for pointing that out because that is good to know. For people who are going to use alloc, that is, you got to keep them out of the loops. You got to keep them only in the thing. Yeah. Well. You learn something new every day. I guess I should have been using alloc a lot more. Although I still don't really, yeah, like I said, I don't use it very often, so yeah, it's not the type of thing that comes up super much for me. Let's see. Can you explain again why our current sound buffer fill is problematic? Yes, let's do that. So we will bring up, again, Paintbrush, which is not the best paint package in the world. We admit that freely. And let's see if I can draw something. I can. So basically, here's what I was saying. So we've got this situation. We allocated our buffer, and that's good. And then what we did is we cleared it to 0, so it's empty, right? And then we started it playing. So now direct sound is playing it through. And direct sound has a play cursor, right? Here's the play cursor. And then it has a write cursor. You know what? I'm going to make this a little easier on myself and just say P. And then it's got a write cursor, W, and it doesn't want us to write in here, right? Because this is the area that it's busy possibly copying out to the sound card. Because remember, this is constantly moving forwards. Time waits for no code, if you will. And then there's the write cursor. So ideally what's happening is we have some place that we want to write our sound to, right? So we have some place we're writing our sound to, okay? So at the start of the code, this is cleared to 0. We start playing forwards. It's playing silence, right? Now we query it and we say, where is the play cursor? It says, well, the play cursor is here. And we're like, okay, we know we have a 60th of a second worth of frame time that we're going to wait for, and then we've got some amount of latency we want. So like ideally, we'd like to write right here, right? That's what we should be doing. We should be saying ideally we'd like to write right here. And then we'd say ideally we'd like to write right here, and we'd like to fill to right here. This is our optimal strategy, right? And then the next time around, we query again for the second frame, and let's say we find out that the play cursor ended up here, right? So it's been playing part of our thing. Now, we don't have the freedom now, right, to just write anywhere we want. We have to write from where we left off to continue our sine wave, and then we say, well, if the play cursor's here, our optimal fill is out to there, or whatever, right? So basically what I was trying to say before is, although our relatively janky code is doing that second part correctly, it's saying, where is the play cursor? Let's figure out where to write to, and we'll fill from where we left off up to there. That's working correctly right now. What's not working correctly is that first time. So the first time through, basically what we're doing is we're going to write from the beginning of the buffer always, which is guaranteed to be wrong and stupid. Because basically what it's going to do is the play cursor is going to be here. We're going to look at it. We're going to say, oh, we'd like to fill to here. Then it's going to fill this whole thing, including the region that direct sound told us specifically it didn't want us to fill. Does that make sense? So what we really want to do, ideally, is we want to make this logic a little more sound and just do the first time through actually realize that we don't have to continue from any particular location and start it up at the right point, right? Hopefully that makes some sense. Let's see. Didn't you say that we should write the sound far ahead of the graphics so that it syncs properly? Wouldn't the current method of updating graphics and sound on the same frame cause some lag on the sound? No. So basically what we're going to do is we'll have the frame, right? And we'll know that the frame is going to be displayed here, right? Here's the frame of graphics. Yeah, like that. So we know we're going to start displaying the frame here. And so we know that we just fill in the audio right here, right? And so we're computing that somewhere back here, which is fine. And then we just make sure that we output each at the correct time. So we'll predict when we're going to flip the frame, we'll line up the sound there, and then we'll go. And again, like I said, this is going to be kind of complicated code. That's why I say our current one is pretty janky, because we're not doing all the stuff we need to do to actually make any of this happen. But like I said, I got to kind of walk us through it a wave at a time to avoid just throwing in a ton of code and then being like, oh, well, the reason this thing is doing this is because this other thing that we haven't talked about, and that, so I can't quite do all of this at once. So we're just starting with the basic one, which is just chasing the play cursor properly, which is now working, and so that we don't get any skips, and that's good. But the startup is wrong, and the alignment is wrong, because we're not actually we're not doing anything intelligent right now to try and sync our audio with our video. And we may not for a while, because that's kind of advanced. Since alloc A is just a function call, how does the compiler know when to free the memory? It's not a function call. So I think that's what I was trying to show before when we stepped in. It's actually an intrinsic to the compiler that tells it to do a specific thing. So it's kind of like RDTSC when we looked at that before. It's basically telling it to do a specific set of CPU operations. In this case, the CPU operation is to enlarge the stack. So it's to move the stack pointer, or the stack top, basically, so it knows that it's using that memory. Let's see. Will we split our game sound updates out of game update and render so that it can be called from a callback or another thread? Yeah, I think so. That's why I was saying earlier, I think I said in the previous stream, that we may eventually have to split it out to fill it on a separate thread. We may decide never to do that. There's plenty of games that ship that don't do that. But if we want to do that, then we'll have to split it up. But I'm not going to split it up until we have to. So according to MSDN, alloc A is deprecated. Should we not use malloc A like it suggests? So as I have amply demonstrated, I never use alloc A really. It's just not something that I ever do. And so like I did not even know that it wouldn't clean it up at loops. I assumed that it would. I don't know the difference between malloc A and alloc A. The fact that it's deprecated and it tells you not to use it suggests that you should probably use malloc A, but I don't actually know what the difference is, you should check them out here if you actually care about that. Like I said, I don't really want to use alloc. I would rather use virtual alloc for all of our memory, including temporaries, and probably will. I tried to show some alloc stuff. I probably just shouldn't have. Sorry to confuse people with that. Like I said, it's not something I use, and so I'm not really in a good position to talk about it any further than just to point out what it did. And it seems like some people on the stream are pretty knowledgeable about it. They're the ones who corrected my bug. So maybe on the forums, someone who is an alloc type person could speak to that. But I don't know. I don't even think I've ever shipped code that had an alloc in it. I've used it a couple times for testing. Like the thing that I was just about to do is something I would do in testing. I guess I just was never unfortunate enough to throw it in a loop. But I never actually ship code that has alloc in it because I almost always have a place that I want my memory to go by the time I'm actually done. So yeah, I'm sorry, I just don't have any experience with it, so I can't help. Tom Forsyth says alloc scope versus function is probably a C legacy versus C++. That's probably true. C++ is more about cleaning things up in scopes, and so it might be old school C. Let's see. Can you provide a log of the chat on the website? There are a lot of good questions here. I don't really want to have to try and maintain that. If someone wants to put up a site that's the chat log, you can do it pretty easily. You can run something like hex chat that just records the log, and then you could post it. So you're more than welcome to do so, but that's probably not something that I will do. Okay, so Plain Flavored, who I'm not sure who that is, but says malloc decrements the stack if the size is less than 1K or calls malloc otherwise. Okay, so basically alloc, that's interesting. So basically what the person on the stream says, and I'm sorry, like I said, I don't know, I'm not an alloc person. But I'll just say what he said in case this helps you understand it, and you can go read the documentation to check. What he was saying is basically malloc basically will actually do a real allocation if you're trying to allocate more than 1K. And then it will automatically insert a free at the end. So that's kind of handy, actually, I guess. I don't know, seems reasonable. It doesn't sound like a problem to me. So I would say, yeah, that does sound kind of cool. I don't know. Like I said, I don't use them. I'm not sure. Can you talk a bit about how you can safely predict where the flip happens so that you can write sound there? Yeah. So basically, what we're probably going to do, and this kind of code is always pretty tough. It's when we actually do it, you'll see I will mess it up a few times, I bet, as I go to debug it. Because if I'm not like basically cheating and looking at my existing code, it's complicated to do this optimally. Basically, here's what you need to do. This is t equals 0, right? This is when the program starts. Sound will start playing basically immediately, so off it goes, right? And it will sort of advance forward in time. Now these, right, ideally are, this is frame 1, right? So this is 1, this is frame 0, this is frame 2. So we will be displaying nothing during this time. Right? We've just started up. We haven't actually done anything. So we're computing frame 1 right here. This is us computing it, right? And what we're going to try and do is flip it here so that it displays right here. And we're going to write sound here, right? So the way we do that is we go, how fast do we think our frame rate will be, right? We compute the frame based on that expectation. So if we're trying to run at 60 frames a second, we basically say, okay, let's plan to do it at 1/60th of a second from now, write the audio into the buffer 1/60th ahead of when we started, right? And assume that it won't catch up before then. We will do the frame, get it ready, and then we will either use the vertical blank to trigger it, or we'll just use the actual RDTSC or query performance counter, probably not RDTSC, query performance counter, to see how much time has elapsed, and when a 60th of a second has elapsed, do the blit right there, right? And we'll have to write some code, the janky code, that basically tries to make sure that if we end up in a situation where we skip, where we miss a frame or something, that the audio doesn't skip, so we might have to write like 2 frames of audio and then overwrite a frame of audio when we aren't skipping. So write ahead and then overwrite, basically. And also to handle when we miss a frame so that we're displaying at 1 frame for 2 frames, that sort of stuff. It's really kind of janky. It's not fun. It's not fun at all. So let's see. Yeah, so in answer to your question, so how we predict where the flip happens, we just use the query performance. We use the timer in the system. And we basically just try to use the timer to predict when that's going to happen. If we have vertical refresh of a vblank, so a sync that we can sync to, then that's good, because basically there's a function that'll wait for that vertical retrace so we know that it's happening. And also when we use OpenGL Direct 3D, we can set it to automatically wait for that. And we can see when that happens. We can time a few of them and see. So we've got some options, but it's really awful. And you'll see when we write it, it's just awful. It's something you wish the operating system would do for you because it's in a better position to do it. We know that you can't really go below 30 frames per second to give the impression of smooth motion. Is there a similar standard rule of thumb for audio latency? Well, I don't know. I think it varies per person, and it depends on the type of game. You know, if you're playing a game where the audio is largely color, it's like things that reinforce what's going on with the graphics, but it's not integral to the great gameplay, you can have pretty high audio latency. You know, if you have like 100 milliseconds of audio latency or something, which is huge, you may get away with that, right? Because the brain kind of does this weird thing where it syncs stuff up that doesn't happen at the same time. It'll sync it up. But 2 things, if your gameplay is based on audio, like you're playing Guitar Hero or something, or if you're just going for that really tight, crisp feel, then the lower the better, really. I mean, if you can get it down, I don't think there's ever a time when you don't feel better about lower latency audio. I don't know. It's tough to put your finger on. I don't know if people have done sort of tests where they've seen how the feel of a game is improved by reducing the audio latency down. But yeah, you'd like it to be 0. You'd like there to be no separation between the frame display and when the audio happens. So. Let's see. AJ Bonkowski says, the reason allocate is deprecated is because it's impossible to implement on some platforms. Also, it has to be a compiler built-in, which is clunky. Lastly, things get tricky when you inline a function with an allocate or use inside a macro. Thus, in C, modern best practice is to use something like GNU obstacks if you really want automatically freed dynamic memory. In C++, you'd probably opt for unique pointer, shared pointer these days. Yeah, and like I said, I agree. I just don't use allocate pretty much in shipping code. So I don't actually know. I can't really say if there's something else that you should use. Yeah, if you're into shared pointer or basically a thing that a C++ class that dynamically frees the memory that it holds when it exits the scope, that's one totally valid solution. Another thing that's nice about it is basically saying, well, you know, can I get temporary memory in general in my system? I don't know. I will show you when we actually get into things. The only reason allocate even came up today was because I thought I might mention it since it's something that's worth knowing. And I haven't gotten to memory stuff yet. So I'm not in a position to use the sorts of things that I normally would use. So I guess what I would say about it is, yeah, just be aware that it's there. It allows you to use the stack in ways that allow you to not have to predict it. But like the people on the stream said, it's a tough guy to ship. It's a tough guy to rely on if you actually want it to always be there. It's kind of unfortunate because it would be nice if there was a good way to treat the stack and memory the same. And allocate kind of does allow you to do that, but it's just in practice, the main thing that killed it always for me was the fact that there was such a small limit typically, or you had to make the stack size huge and there was all these sort of constraints on it. That was always the thing that killed it for me. But if I was like in charge of how C should have been implemented, I probably would have done things so that allocate could do huge allocations. And you could have done it so that like the program stack was a giant memory stack, and it worked a different way. Like, so I would actually like to have a real alloc, but alloc isn't really that thing, and so as a result, I've never actually used it in shipping code because I never was comfortable with it. Yeah, and like you see, I didn't even know when its cleanup rule was. I would have thought that I didn't realize that I'd put it in a loop. I wasn't thinking about it at that time, but even if I had, I would have thought that it would clean up at the end of the loop because I would have figured that what the compiler would do is on entering the loop, push the stack frame down, on exiting the loop, pop it up. And to be honest, I have no idea why you wouldn't just do that, but I guess it makes things too complicated for the compiler because it has to remember where it's basing things off the stack pointer or something. I don't know. It doesn't seem like it should be, but you know, maybe it is. Oh, and AJ Bonsky, I know you weren't picking on my style. Like I said, I don't use alloc, so it's not picking on my style at all. The last thing I would do is recommend people use alloc because I have no experience with it shipping code, so I have no idea. I was just saying, you know, it's there. Be aware of it. It allows you to grow the stack size dynamically, and it looks like, I guess from what people are saying, that maybe you can't use it very effectively on their platform. So that's maybe one good reason not to. We won't be using it in any of the final code of Handmade Hero because it's just not something I do. Yeah, but like I said, I try not to be ideological on the stream, so I try not to say stuff like don't use alloc, because how should I know, right? Especially things I don't have much experience with, like alloc or other sorts of things. I'm not in a position to tell you, do use this, don't use this. Usually all I can really do is say, here's what I do, here's what works for me, here's some trade-offs about them, make your own decisions. And for something like alloc, like I said, yeah, I couldn't say that. So I don't use it, but I wouldn't say don't use it. I'd say go learn about it yourself now that you kind of know about it and see what you think of it. And like I said, there's a lot of people on the stream who seem to have more experience with it than I do. Maybe if they're on the forums, you guys could discuss it, and they could tell you a little bit about why they don't or do use it, and you know, stuff like that. How would you do 2 voices with sound waves in 1 buffer? Well, we will be doing that. Just you wait. Let's see. When will be the first sprite display in animation? Who knows? When we get to it. When we get to it. Depends how long things take to explain. Let's see. I've heard the brain treats sounds within 10 milliseconds as happening at the same time. I suspect audio to video sync is the same. No, I don't think that's true. I think you can be way further off than 10 milliseconds in audio video sync. But I could be wrong about that. Getting less than 10 millisecond latency would be great, and you would love to have that. A lot of times I don't think you realistically get it, but that would be cool. When you work with temporary memory, is there a risk of memory overflow and memory leaks? If so, how do you make sure these don't happen? So yeah, I mean, memory, basically, anytime you're managing memory, it is definitely something that you have to be aware of. Typically, the way that I approach those problems, and you'll see me do this, like I said, I haven't gotten to the point where I've talked to you about memory yet, so we really haven't had a chance to do any of the things that I would normally do. But we're getting there. In fact, it may be Thursday that we do it. The thing to understand is managing memory actually isn't that hard once you build some tools. We haven't built the tools yet, so it'd be pretty hard now. But once you have some tools for it, you'll see it's actually not that hard. But yes, anytime you're doing low-level programming, even if it has nothing to do with memory, let's say you're just trying to fill in a buffer that's just some array someone made. If you're not careful, you could write off the end, write off the beginning, who knows. There are tricks for catching those sorts of things as well. You saw the compiler catch one of ours today, but there's another way you can do it too, and I'll be showing you that. It's basically with virtual alloc, you can line things up so that if you write even a single byte off the end of something, you'll fault immediately, and that's a good way to catch things too. But there's a lot of stuff that you have to do basically to make sure that you can run in debug mode with that, but then run in non-debug mode without having all the overhead of doing the lines up like that. So we'll be getting to those things. Let's see. I'm a long-time rhythm game player, and I can notice audio off-sync as little as 10 milliseconds early or late. Getting it just right is both a big deal and possible. Yes, and I agree with that, like I said. The problem is it's really not possible, though, because even if you get it right on the output, which is what we'll try to do, your TV may delay it, and you may plug it into a receiver, and the audio plays on a delay that's different from the video. So it is very problematic getting below 10 milliseconds if you don't have some way to really calibrate your actual setup. So we can do stuff to try and get it so that we are outputting things at the right time, but that doesn't really help the actual real world result, unfortunately. Okay, we're getting to the end of the stream here. Last couple questions. Let's see. Any advice for a senior level CS student interested in game development? Sorry, if you want to ask those kind of questions, maybe we can do that on some kind of a stream that's not programming oriented. Because basically those questions are kind of general, and I'm not even a good person to answer them. But in the pre-stream, before the stream starts, we'll do questions sometimes of that, and I can answer them to the best of my ability. But I don't even really know answers to questions like that. Let's see. I think that's roughly it. Do I see anything else on here? I don't see anything else on here. Let's see. I think that's about it. All right, ladies and gentlemen, thank you very much for joining us for another edition of Handmade Hero. I think everything besides our attempt to show Alec A today, which was kind of terrible, although the folks in the stream kind of saved it for us, so thank you very much for that. Basically, that would have given people the wrong impression of Alec A. Now they've kind of got the right impression of that's good. But basically, ignoring the Alec A-ness today, I think we did a pretty good job of doing what we set out to do, which was abstracting more of our platform layer. We've now gotten to the point where we're all good with audio happening on the other side. So we need to do some work on our platform layer to make the audio output actually synced more properly with the video, which is something I want to do. But we'll hold off on that for a little while. Tomorrow we're going to do input, and then the day after that we'll do memory, and then we'll be in good shape for actually starting to write some game code, or going in and tightening down a few of those platform things, which is maybe what will take some time to do, just so we can really solidify that platform layer and kind of be done with it for a while, put it aside, and move on to actually writing the game code. So thank you so much for joining us. It has been a pleasure. Thank you very much to the people on the stream who corrected the Alec A stuff. I could not do it without you guys, because like I said, when I'm programming on the stream, it's tough up here. It is definitely tough. And especially when I'm working with some stuff and I want to point out something that isn't something that I do frequently, it really helps to have other experts on board who can say like, oh, you should know this, or take a look at that. That's pretty helpful. So thank you guys for that. And if you do have time to post on the forums, that would be great too, to fill in some of that knowledge. If you go to handmadehero.org, there's this news and forums button here. You click on that. And you can get all the stuff. You can get the episode guide, which is pretty cool, but you can also go to code discussion, where we've got a bunch of stuff there. So thank you so much, everyone, for joining me, and I hope to see you tomorrow at 8 p.m. PST, when we will tackle input and maybe memory. I don't know if we'll get to it. We'll do input and memory over the next 2 days, but how much we get to tomorrow, I can't say. So thank you very much for joining us, and I will see you tomorrow.